Hello my dear students, in this lecture we are going to see Einstein coefficients. Einstein's coefficient A and B. Now here we have to develop the relation between Einstein coefficient A and Einstein coefficient B. Now this lecture is very much important for any competition as well as for all the universities. In India, if you go in any university, there will be definitely question on this Einstein coefficients. So my dear students, this lecture is very much important, right, for physics. Now see, for understanding of this Einstein coefficient A and B, you need proper and in detail understanding of these four topics. And these four topics already we have covered in previous lectures. Again in this lecture also, whatever the required part from this topic I will revise, right. So here the first important topic is rate equations for absorption, spontaneous emission and stimulated emission. This is very important for proper understanding of this Einstein coefficients. Then the thermal equilibrium concept and equation of Goldmans distribution law. Means Goldmans law is also important and Planck's radiation law is also important for developing relation between A and B, right. So my dear students, here first of all we will start with basic concept of absorption, spontaneous emission and stimulated emission. So my dear students, to understand properly the absorption, spontaneous emission and stimulated emission, we have to understand the interaction of radiation with matter. Now here, to understand this interaction of radiation with matter, now what is matter? Matter is nothing but it may exist in solid, liquid and gaseous phase. Therefore, the matter is nothing but solid, liquid and gaseous phase. And my dear students, the matter is always made with the help of molecules and atoms. So in matter, there are n number of atoms, right? So my dear students, here basic atomic model we have to understand the interaction of radiation with matter, right? Now here, if I show you atomic model, let us say this is the center of atom and the center of atom is called nucleus, right? The center of atom is called nucleus, and nucleus contains photons and neutrons. Nucleus contains photons and neutrons. Photons means positive charge and neutrons means no charge, right? Zero charge. On photon there is a positive charge, on neutron there is a no charge. And around this nucleus, the electrons are revolving. So here if I want to show you orbits, see this is the first orbit. Let's say this is the first orbit. In this orbit the electrons are revolving and the first orbit is named as K orbit. Then there will be a second orbit in which also there are number of electrons, right. This second orbit is named as L orbit. Then there will be third orbit, that is M orbit, then N orbit. Similarly there are more orbits depending on the number of electrons. As number of electrons goes on increasing, number of orbits goes on increasing, right. This is a M orbit. After M there is a N orbit, so on, right. Now my dear students, again for the orbits there is a principal quantum number. Let us say here I will write there is a principal quantum number. Principal quantum number is generally represented by N. And my dear students, the maximum possible number of electrons in any orbit is nothing but number of electrons means it is a maximum possible number of electrons that can exist in particular orbit. These circles are orbits, and in these orbits the electrons are rotating or revolving around this nucleus. Now you can understand, let us say this nucleus is the sun and earth and other planets are revolving in the orbit around this sun, right. Now number of electrons likewise you can understand, right. Now number of electrons is equal to, this is nothing but twice n square, where n is principal quantum number. For first orbit principal quantum number is 1, means here for when your k n is equal to 1. For second orbit principal quantum number is 2. For third orbit principal quantum number is 3. For fourth orbit there is n, principal quantum number will be 4, and so on. This is how we have to write. Now my dear students, so here we can say the maximum possible electrons in the first orbit will be 2 into 1 square, that is 2. Therefore here if I show you the electrons with red color, let us say here I will show you red dots for the electrons. Here there will be one electron, other electron, right. These are the electrons, right. This is the electron having negative charge. Therefore in K orbit the maximum possible electrons will be 2. Similarly in L orbit principal quantum number is 2. 2 square is 4 into 2, 8. Means in L orbit the maximum possible electrons can be 8. 1, 2, 3, 4, 5, 6, 7, 8. Likewise there will be maximum possible electrons will be 8, right? Therefore here I can write 8 electrons. Similarly, in m orbit, principal quantum number is 3, 3 square is 9 into 2, 18. In m orbit, there will be 18 electrons. This is the maximum possible number of electrons, right? And my dear students, here as electrons are revolving around the nucleus, whenever there is any activity, there is an energy, right? Therefore, my dear students, here in every orbit there will be energy. Let's say in first orbit energy level is E1. In second orbit, let us say energy level is E2. In third orbit, let us say energy level is E3, and so on, E4, E3, E4, E5, E6, so on. As orbit goes on, energy level goes on increasing. And see, my dear students, as the number of electrons increases, definitely energy is going to increase. Means whenever number of electrons are more, then energy is also more, and vice versa. Number of electrons are less, energy is less. In first orbit, electrons are only 2, therefore energy is E1. In second orbit, electrons are more, energy will be more. Means here, what will be the relation? Energy in first orbit is less than energy in second orbit is less than energy in third orbit is less than, so on, right? And so on, right? Means in nearest orbit, energy level is less as compared to the outermost orbits, right? And my dear students, here as energy increases, energy is nothing but, see, energy is nothing but whenever more energy, there will be more motion. Whenever there is a more energy, then there will be more motion, means there is more unstable condition, right? Energy is more means it is an excited state. More energy means it is an excited state, and means it is an unstable state. Unstable state. And less energy means it is a more stable as compared to higher energy. Lesser energy zone is more stable as compared to higher energy level, right? And my dear students, naturally the motion is always from high energy to the low energy. Naturally the motion is always from the high energy to the low energy. Now my dear students, again one more terminology you have to understand, that is nu. Here it is nu. Nu is nothing but radiation frequency. Nu is radiation frequency, right? This is important, or also simply called frequency of radiation. And my dear students, the energy in one photon, if I give one photon, right, in one photon the energy E is nothing but h nu. This also you have to understand from the basic understandings, right? One photon contains the energy of h nu. Now with the help of this E1 and E2, let us say energy levels, I will consider this energy level E1 and energy level E2. E2 is more than E1, so I will show it diagrammatically. So let us understand, let us say here there is a energy E1, right, and there is a energy E2, and we know that energy E2 is more than energy E1, right? Therefore here we can say it is ground state. This E1 having lower energy is called ground state. It is called ground state, or it is called more stable state as compared to this. Therefore this E2 is nothing but higher energy, therefore it is an excited state. It is an excited state or higher state, or also called higher level of energy. And this is a lower level of energy, lower state or lower level of energy, higher state or excited state or higher level of energy. Now my dear students, let us say, now here first of all I will explain you what is the absorption and emission. Now whenever any electron, let us say there is an electron, if any electron moves from lower energy level to the higher energy level, now this electron here, electron from the lower energy level is moving towards higher energy level, then this process is called absorption. This process is called absorption. And my dear students, whenever any electron moves from excited state or higher energy level to the lower energy level, then this process is called emission. This process is called emission, right? And now my dear students, for this absorption and emission, there is only one absorption, and there are two types of emission. That is here spontaneous emission and stimulated emission. So we have to understand the absorption as spontaneous emission and stimulated emission. So let us understand one by one. Now let us say here there is an energy level E2, and here there is an energy level E1, right? There will be electron in lower energy level as well as in higher energy level also there are electrons. Don't worry about that. Now naturally the motion is always from higher energy level to lower energy level, but against nature, if I want to do some operation, then I have to give external energy supply. Against nature, if I want to do anything, then I have to give external energy supply. So what I will do, this difference of energy is nothing but E2 minus E1, because E1 is more than E2. This is the difference of energy is equal to E. Now what I will do, I will supply one photon of having energy equal to difference of this energy level, and the photon energy is nothing but h nu. This is a photon energy. Now what I will do, I will give one photon to the lower energy level. This is a photon, right? I will give one photon to the lower energy level of energy h nu, right? Now my dear students, because of this external energy source, this lower energy electron, this electron in lower energy state or ground state will get excited to travel towards the higher energy state. Now therefore it will get excited to travel towards higher energy state, and the process is called absorption. The process is called absorption, right? Now again, similar to the absorption, there is an emission also. Similar to the absorption, there is an emission also. Now let us understand the emission. Now my dear students, for the emission again, there are two types of emission. See, for this each and every theoretical point already I have explained in previous lectures. For proper and better understanding, you can go in, watch my previous lectures, or simply understand here also. Here my basic assumption is that you know all the basic terminology and you have seen my previous lectures, and then only you came for understanding of this very important topic, Einstein coefficient, right? Now my dear students, let us say after this absorption, now this electron is moving. Now here only one electron I am considering, right? After absorption condition I am showing you. See, this is a E2, this is a E1, right? Now after absorption, the electron is now in higher energy level. Here this electron is at higher energy level, right? Therefore this is the electron. But my dear students, naturally always electron tries to move from higher energy level to the lower energy level. Now whenever this electron is moving from higher energy level to the lower energy level, this is called emission, and there are two types of emission. That is, one is spontaneous emission, one is spontaneous emission, right? And my dear students, this spontaneous emission is a natural process. Natural process means, see, whenever any electron presents in excited state, these electron always try to move towards lower energy level, and the life of this electron in the excited state is only 10 to the power minus 8 seconds. This is the life of electron in excited state, right? Means this electron in excited state can stay only for 10 to the power minus 8 seconds, and after this time, this is called lifetime of electron. After this time, the electron again moves to the lower energy state on its own. On its own, it is moving towards lower energy state, and during this process, there will be one photon is emitted of energy h nu. This one photon of h nu magnitude of energy is emitted, right? Which is nothing but difference of this energy level, E2 minus E1, right? And this process is called spontaneous emission, right? On its own, after 10 to the power minus 8 seconds, after staying for 10 to the power minus 8 seconds in the higher energy level, it is moving towards lower energy level. This is called spontaneous emission, right? And my dear students, again there is one more type of emission, that is called stimulated emission. See, in higher energy level E2, there is a one electron after absorption. It is a condition after absorption, right? There is an electron, right? Let me show this electron with blue dot, right? Now what I will do, in a stimulated emission, second type of emission we are understanding, that is stimulated emission. Stimulated emission. Now my dear students, in stimulated emission, this electron in the higher energy level is again given energy, external energy of magnitude h nu, that is one photon energy. Again here the electron in higher energy level is given external energy source from the photon of magnitude h nu, right? And this is nothing but E2 minus E1. Now because of this external energy level, this photon or this electron is excited to travel towards lower energy level, and it is going towards lower energy level, and this is also emission. And during this emission, see, whenever the electron is traveling from E2 to E1, there will be a one photon emitted of magnitude energy level h nu. But we have supplied one more external photon, so this external photon is also emitted here, also traveling in forward direction of magnitude h nu. Means in case of stimulated emission, there is two photons are released. If one electron is moving from higher energy level to lower energy level, two photons are released. There will be an emission of two photons, right? This is called stimulated emission, or also called forced emission. This is also called forced emission, because external energy level is given here, right? And my dear students, here one point I want to tell you that, see, whenever external energy source is used, then the Einstein coefficient is written as B, right? Here B is Einstein coefficient, B is Einstein coefficient, and this B is nothing but, let me write this Einstein coefficient. It is the Einstein coefficient if external energy source is used. External energy source is used. This is very important. This is very, very important, right? Means here, see, for absorption, always I am using external energy source, and for stimulated emission I am using external energy source. Means in case of absorption and stimulated emission, the Einstein coefficient is B, right? And if external energy source is not used, then the Einstein coefficient is A, right? Therefore here I will write A is Einstein coefficient if external energy source is not used. External energy source is not used, right? And in case of spontaneous emission, that is natural emission, without external energy source, here you can see, without external energy source, on its own, because of energy difference, the electron is traveling from higher energy level to the lower energy level. So it is here the coefficient will be A. Einstein coefficient is used A, and we have to develop relation between B and A. So my dear students, after basic understanding of this absorption emission concept, write down now Einstein coefficient A and B. Now my dear students, to understand this Einstein coefficient A and B, first point we have to understand the rate equation of absorption, right? So write down rate equation of absorption. Again, after that we are going to understand rate equation of emission also, right? Now my dear students, already we have seen absorption is nothing but, let us say this is a higher energy level E2 and there is a lower energy level E1, right? Now here in lower energy level, one electron will be there will be n number of electrons, but if for this particular electron, if I supply external energy source of photon of magnitude h mu, right? My dear students, this lower energy level electron will get excited and travel towards higher energy level, and will stay in the higher energy level for 10 to the power minus 8 seconds, right? This process is called absorption, right? And now my dear students, here I am using some terminology. Here this mu is nothing but radiation frequency, already we have seen. Now let us say n1 and n2, I am again using the notations n1 and n2. Here for lower energy level n1 and for higher energy level n2, where let me write first what is this n. N is nothing but population density. This is population, or simply called population, right? Now if I write n1, it is a population at lower energy level. It is a population at lower energy level, also called ground level. So you can write here ground level also. Lower energy level is also called ground state or lower state, and higher energy level is also called excited state. So my dear students, another En2 is nothing but same population at higher energy level or excited state. Right. Now my dear students, here again I am using one notation that U omega is nothing but energy density. It is energy density. But my dear students, it is an external energy density. If external photon energy is given, there will be external energy density U omega. Right. Now here let us understand this rate equation of absorption is nothing but, see, which electron is traveling here? The electron which is at ground state, that is the population at ground state is going to decrease. This n1 is going to change, because the electron at ground state is traveling towards higher state or excited state. Therefore this population at ground state is going to decrease. Therefore here the rate equation for absorption is in terms of n1, right? And rate is nothing but with respect to time. Rate is always with respect to time. Therefore this rate equation is dn1 divided by dt. dn1 by dt is nothing but rate equation of absorption. So I will write here for absorption dn1 by dt. So rate equation for absorption is written in terms of n1, right? Now because energy is given to the electron which is present in lower state or ground state, right? And this is written as, this will be equal to n1, that is population at lower level energy level, into Einstein coefficient. Now Einstein coefficient will be, whenever external energy supply is given, then Einstein coefficient is B. But now the motion of electron is from state 1 to the state 2. This will be the direction of motion. Therefore it will be B12. Whenever external energy level is used, external energy is used, then we have to multiply with energy density also, right? That is U omega. We have to multiply with U omega also, right? And this is the my rate equation for absorption. This is the first equation. Now this is also we have studied previously, right? So remember this rate equation for absorption, very important equation, because later I need this equation after understanding thermal equilibrium conditions, right? Now after understanding of this, let us understand the rate equation for spontaneous emission. So next, second, write down rate equation for spontaneous emission. Spontaneous emission, right? Spontaneous emission means on its own, right? Here no external energy is used, means the Einstein coefficient used is A, right? Let us say here it is a E2, that is excited state, E1, that is ground state. Therefore here population will be N1, here population at higher energy level will be N2, right? Now after absorption, now the electron is in higher energy level, right? This will be state of electron after absorption. Now after staying in the higher energy level for 10 to the power minus 8 seconds, on its own this electron will move towards the lower energy level, right? And during this there will be an emission of one photon of energy level h nu, right? And my dear students, this is called spontaneous emission, that already we have learned, right? Now my dear students, again during this process, see, now from where to where the electron motion is there, from state 2 to the state 1 there will be electronic motion, right? Therefore the rate equation is written in terms of n2, right? Because the motion is from 2 to 1, therefore rate equation is written in terms of n2. Now my dear students, here there is no external energy supply is used, therefore the coefficient will be A. Therefore here this dN2 divided by dt, this is called rate equation. But for here spontaneous emission, will be equal to again N2 into Einstein coefficient A, but here the Einstein coefficient will be from 2 to 1, it is from 2 to 1, A 2 to 1, and there will be no energy density because external energy source is not used, therefore this U omega will be 1. There will be no external energy density. That's why this will be our rate equation for spontaneous emission. This is, let us say, equation number 2. For this equation I am writing as equation number 2. Now similarly, let us write down the rate equation for stimulated emission. The third equation I am writing, rate equation for stimulated emission. Now my dear students, for stimulated emission, rate equation is nothing but the motion of electron from the excited state to the ground state is due to the external energy supply. Therefore here if I show you diagrammatically, see here N2 in higher excited state, N1 in lower state, that is population in higher state and population in lower state. Now after absorption, now electron is in higher energy level, right? This will be the electron in higher energy level after absorption. Now my dear students, if I give external energy supply of photon of magnitude h nu, right, then this electron will get excited to travel towards lower energy state or ground state, and during this process, see, one photon is emitted of magnitude h nu energy, and this supplied photon is also traveling, right, in the same direction of magnitude h nu. Means for one input there are two emissions, right? Now my dear students, during this process, see, now again the motion is from higher energy level to the lower energy level, therefore the equation, rate equation will be written in terms of n2, right? Now, and as motion is from 2 to 1, the constant will be, and external energy source is used, then constant will be B2 to 1, right? Therefore the rate equation is dN2 divided by dt, but it is for stimulated emission, is equal to, see, N2, because the motion from N2 to N1, N2 into, now here external source of energy is used, therefore Einstein coefficient will be B, but it is moving from 2 to 1 into, we have to use the energy density also, U omega, because external energy source is used, right? This will be our rate equation for stimulated emission, and this is my third equation. This is my third equation. Now all the three equations are very much important, right? What was the rate equation for absorption? Rate equation for absorption was dN1 by dt of absorption is equal to N1 B12 U omega, right? This was the equation number 1. These three equations are very much important. Now before understanding how to combine these equations, let us understand what is the thermal equilibrium. Now my dear students, thermal equilibrium is nothing but equality of temperature, means at each and every location the temperature is same. Now let us understand this concept thermodynamically. See, let us say you have one room, let's say this is your room, right? And in this room, if you keep one ice, let us say this is the ice. Again, if you keep one water, let us say this is the water, or let us say hot water. In the same room, I am keeping hot water. Now let us say the temperature of ice definitely will be less than temperature of room, and this room temperature is less than temperature of hot water. Temperature of hot water. This is my relation. Initially, at the when time is 0 second, the condition is temperature of ice is minimum as compared to room temperature. Here temperature of hot water is maximum. Now my dear students, after some time, we can say after some time, these three bodies will thermally interact with each other. Room, ice and water will thermally interact with each other, and after some time the temperature will become same. Temperature will become same. This condition is called thermal equilibrium. This condition called thermal equilibrium for these all three components. Right. Now my dear students, so for thermal equilibrium, the ice temperature will increase, and hot water temperature will decrease, and all three will achieve final equilibrium temperature. This is called thermal equilibrium. So my dear students, for thermal equilibrium, the temperature at each and every location is same. So again, for thermal equilibrium, here I can write, see, similarly for higher energy level E2 and lower energy level E1, how to show this thermal equilibrium? See, whenever there is a motion of electron from lower energy level to the higher energy level, this is called absorption. And whenever the electron moves from excited state, that is higher energy level, to the lower energy level on its own, then it is called spontaneous emission. And whenever electron moves from higher energy level to the lower energy level with the help of external energy supply, then it is called stimulated emission. Now my dear students, again for thermal equilibrium, we can say for thermal equilibrium condition of these two states, right? Then I can write the number of upward transitions here. Number of upward transition, we can say for number of upward transition will be equal to number of downward transition. This is called thermal equilibrium condition, right? Whatever may be the upward transition must be equal to downward transition. Means one electron, if two electrons are moving in upward direction, then there are two electrons moving in downward direction. If three electrons moving in upward direction, three electrons will also come in downward direction. This is called thermal equilibrium condition. So my dear students, therefore here we can say the rate equations are same. Or equal. So how to write these rate equations? See, now my dear students, what is the, for upward transition, what is the rate equation? dN1 divided by dt, that is for absorption, must be equal to. For downward transition, what is the rate equation? For spontaneous emission, it is dN2 divided by dt of spontaneous, plus for stimulated emission it is dN2 divided by dt of stimulated, right? This is called equilibrium condition. So my dear students, this condition is called equilibrium condition. So already we have derived the equations, or we have seen these equations. So put these equations. So my dear students, dN1 by dt of absorption is nothing but N1 B12 U omega, that already we have seen, is equal to dN2 by dt of spontaneous emission is nothing but N2 A221 plus dN2 by dt of stimulated emission is nothing but N2 B221 and U omega, right? This already we have seen. Now what I will do, I will find here this energy density U omega. From this equation I will find the relation for energy density U omega. So my dear students, how to write? See, let us take this term on left side. Right. Therefore, it will be written as n1 b12 u omega minus n2 b221 u omega is equal to n2 a221. Right. Now let us consider u omega common, that is energy density common. Therefore, it will become n1 b12 minus n2 b21 is equal to n2 a21. Right. Now let us take this term on the another side. Right. Therefore, this u omega will become n2 a21 divided by n1 b12 minus n2 b21. Right. Now my dear students, again for this equation, what I will do, I will divide numerator and denominator with n2. There is no problem, absolutely fine. If I divide numerator as well as denominator with n2, there is absolutely fine. Therefore, again what this u omega will become, it will become a21 divided by n1 divided by n2 b12, it is b12 minus b21. Right, this will be our fourth equation, because already three equations we have written. Let us write down this equation as fourth equation. Right, now after writing this fourth equation from the thermal equilibrium condition, we have to use now Goldmans distribution law. Now my dear students, from the Goldmans distribution law, this population n is represented in terms of some parameter. This population n is nothing but n naught e to the power minus e divided by kt. Right, this is a Goldmans distribution law. So my dear students, hence with the help of this law, I can write n1 is equal to n naught e to the power minus e1 divided by kt, and n2 is equal to n naught e to the power minus e2 divided by kt. This minus e2 by kt is nothing but in power, is power. Right. So let us find this n1 by n2 to put in this fourth equation. Therefore, here I can write n1 by n2 will be equal to n1 is n naught e to the power minus e1 by kt divided by n naught e to the power exponential power minus e2 divided by kt. Right. Now my dear students, here n naught will get cancelled. N naught will get cancelled. Right. And this power will go up and it will become positive power. Right. So, and this is a negative power of the same e. Therefore, simply here school level mathematics I am writing n1 divided by n2 can be written as, see, e power here e2 minus e1 divided by kt. E power e2 minus e1 divided by kt. This is how we can write. And my dear students, what is this e2 minus e1? It is the energy of one photon, h nu. This is the energy of one photon, already we have seen, h nu. Therefore, the same equation can be written as this n1 divided by n2 is nothing but e power, here it will become e power h nu divided by kt. Right. Let us put this n1 by n2 in this fourth equation. Then you will get one fifth equation. Therefore, this u omega, that is u omega is nothing but energy density, is equal to a21 divided by n1 by n2 is e power h nu divided by kt, right, into b12 minus, in the denominator only, minus b21. Right, this is how we will get one more equation. Now here from the denominator, let us consider b12 common. Therefore, this equation will become u omega is equal to a21 divided by b12. Now if I consider b12 common, it will become e power h nu divided by kt minus b21 divided by b12. Right. Now my dear students, this will be our new equation. So already we have written fourth equation. Let us write down this equation as fifth equation. I will say this equation is my fifth equation. Now after this fifth equation, we have to equate this equation with the help of Planck's radiation law. So let us understand Planck's radiation law. Now my dear students, with the help of Planck's radiation law, we have this law. You must remember this law. See, from all basic concepts, all the previous concepts I am using here, directly I am exporting the law from the previous lectures. U omega is written as 8 pi h nu cube divided by c cube into 1 upon e power h nu divided by kt minus 1. Here minus 1 is in the denominator only, right? This is the Planck's radiation law. Let us say this law has a 6 equation, right? Now let us compare these two equations. What I will do, I will compare here this Planck's radiation law, right, with the equation number 5. Let us equate or compare these two equations. Now if I compare these two equations, see a21 divided by b12, this factor I will get this equal to this factor, right? Therefore here I am getting relation between a21 divided by b12 is equal to 8 pi h nu cube divided by c cube, right? Let us say this is our seventh equation. This is our seventh equation. Again, my dear students, again by equating these two equations, see this b21 divided by b12 we will get equal to 1, right? Therefore from the equation comparing these two equations, I will get b21 divided by b12 is equal to 1, right? That means after cross multiplying here, I will get b21 is equal to b12, right? This will be my 8th equation. Means here the if external energy source is given, the Einstein coefficient in both direction is same. Einstein coefficient in both direction is same. b21 is equal to b12, right? And between a and b the relation is here 8 pi h nu cube divided by c cube, right? Now my dear students, from this equation can I say the Einstein coefficient a21 here, Einstein coefficient a21 is directly proportional to nu cube, and nu is nothing but radiation frequency. Therefore this a21 is a very strong function of radiation frequency, very strong function of radiation frequency. This is also important, right? And my dear students, each and every point and each and every relation is very much important for competition as well as for any university in the India. Thank you, dear students. In next lecture we will see one more topic from the chapter, that is requirements for laser production.